Okay, so I realize this might be tough to read, but we'll do our best. We got a binary cycle, so I've got steam here and R134A here. Basically, Q out of the steam is Q in to the R134. Okay, and I've got lots of pressures and temperatures given. This is all ideal, so everything's isentropic and all that good stuff. So we'll start up here where it says the pressure is 40 bar and 440 degrees Celsius for steam. So I go right here, 40 bar, 440, and I get H equals 3307 and S equals 6.904. Okay, so let me go ahead and jot those guys down. So that's 3307.1 and S1 is 6.9041. Again, isentropic across the turbine, so that means S2 is also 6.9041. That pressure is at 1 bar. So I go over here to 1 bar, and I'm looking for about 6.9 S. So at 1 bar, you can see that saturated vapor is 7.36 about. So I'm a little bit below that, so I can actually look up the enthalpy, do the interpolation, and I get 2505.7 for H2. Okay, going on to state 3, this is saturated liquid at 1 bar. So I'm going to look up my H value there. So at 1 bar, saturated liquid is 417.46. I will also need the specific volume of this because I'm going to use that specific volume to deal with the pump, and that's 0.0010432. So let me go ahead and jot those down. So again, H3 is 417.46, and this should actually be V3, which is also equal to V4, I guess, at that point. But anyway, V3 is 0.0010432. Okay. Now for the pump, you'll remember that, again, V times delta P, V2 minus P4 minus P3, excuse me, equals H4 minus H3, right? And again, that's because it's a isentropic, steady state, incompressible flow sort of thing. So it's V times delta P equals delta H. So using that, I can calculate H4, and I find H4 to equal 421.53, thus setting my steam cycle. Now I'm going to move on to my refrigerant cycle, where A is at 16 bar and 100 degrees Celsius. So now I'm going to flip over to 134A. I'm going to 16 bar, which is right down here, and what was it, 100 degrees Celsius. So H is 327.46 and S is 1.0467. So I'm going to jot those guys down. So H is 327.46 and S again is 1.0467. Again, that turbine is also isentropic, so that S is constant. So SB is also 1.0467. Its pressure is 9 bar. So I'm going to come over here to saturation, 9 bar, and again my S was 1.04. Okay, I'm actually above that, so I need to go into these tables for 9 bar. Okay, I have 9 bar right here, and again my S is 1.04, so I'm somewhere in between here. You can do the interpolation, and I get 312.74. Okay, going to state C, I'm at 9 bar. Now I'm a saturated liquid, so I'm definitely going in here as a saturated liquid. My H value is right here, 99.56, and again I'll need my volume for the pump, which is going to be 0.0008576. So let me go ahead and jot those down. So HC equals 99.56, VC equals 0.1238576. And again, same idea. This is an isentropic pump. So VC equals the change in pressure. Oops, not equals. Multiplied by the change in pressure. That equals the change in enthalpy. Again, I know volumes and pressures. I can then calculate HD. I find HD equal to 100.16. And that sets my states. Okay? So again, knowing a lot of this stuff over here using isentropic conditions, I can figure all of those states out. Now the first thing I want to find are my mass flow rates. I know Qn is 13 megawatts. So I'm going to use that to calculate the mass flow rate of the steam. So again, Qn is given to us. It's the mass flow rate of the water times H1 minus H4. So again, Qn is 13 megawatts. H1 and H4 are calculated for me. From that, I can then calculate the mass flow rate of the water, which is 4.505, and that would be kilograms per second. Okay. Now, going over to the refrigerant, now I know the mass flow rate of the steam. Its Q out is actually Q in to my refrigerant. So that means that the mass flow rate of the water is Q out, which is basically H2 minus H3. That's Q out of the water. That equals Q in of the refrigerant. So that's the mass flow rate of the refrigerant times HA minus HD, right? Which is Q in to the refrigerant. So out of this equals in of that. I know all of my H values. I know the mass flow rate of the water. Therefore, I can find the mass flow rate of the refrigerant to be 41.39 kilograms per second. Now that I have my mass flows, I can actually figure out the work of each cycle. So I can find the work of the water, which is going to be the mass flow rate of the water that I just calculated, times the work of the turbine, H1 minus H2, minus the work of the pump, which is H4 minus H3. Right? So I've got that mass flow rate of the water, turbine minus pump. That gives me the work of the steam equal to 3,592. And that is in kilowatts. Work of the refrigerant power cycle, I take the mass flow rate of the refrigerant times the work of the turbine, which is HA minus HB, minus work of the pump, which is going to be HD minus HC. Again, knowing all of my H values, knowing the mass flow rate of the refrigerant, I can find that the power developed by the refrigerant is 584 kilowatts. Okay. So now you can see why this binary cycle is helpful, because ordinarily I would have just dumped the heat from the turbine into the atmosphere, the environment in some way. Instead, I dump it into the refrigerant cycle, and I get an entire 584 extra kilowatts of power for the same amount of input. So I've improved my performance by, rather than dumping again just into the environment, dump it into a cycle at lower temperature, get a little bit more power out.